by thanking the organizers, especially Tufik, for the invitation to speak. And I should also mention that this is all joint work with Foster Tom at MIT. And the big message of this talk, which I hope you take away, if you take away nothing else, is that if you want to work with the chromatic symmetric function in a particular basis, it may actually be easier to express it in a different basis where you have more control and then do a basis change. That's the big idea. And here's an outline of the talk. We'll first talk about the monomial basis, and this will include an introduction to chromatic symmetric functions and all the stuff we'll need to know about symmetric functions to understand the talk. We've seen symmetric functions in many previous talks, so some of this is going to be review, and for you, the experts, you can probably work on something else for the first 5 minutes and you won't miss anything, but tune in later. And then the basis that we're really interested in because of the Stanley-Stembridge conjecture is the elementary basis. So then in the second part, we'll do the basis change, see what we get. And then third part, I'll give you some comments. So to start out. So we're doing chromatic colorings of graphs. So G is going to be a graph with vertices V and edges E. P will be the positive integers, and you've got a set of variables, boldface X, indexed by those positive integers. And therefore, if we have any coloring, that is to say, a function from the vertex set to the positive integers, we can associate with that a monomial in kind of the obvious way. You just take each time a color appears as an image, you use X of that color. So if the color I appears, you'll have an X of I in your product, and you keep track of multiplicities. So if, color I appears 5 times in the function, then you're going to get xi to the 5th. And of course, as often the case in graph theory, we're concerned with proper colorings, which are those such that if I have an edge UV, the colors of its endpoints are different. And from this, we get Stanley's chromatic symmetric function, x of g, or if I want to be more specific, x of g, boldface x. And it's just the generating function for all proper colorings using the positive integers by summing up all these monomials, one for each color. So in case you haven't seen this before, let's do a quick example just so that you can get a feel for what's going on. So there's my graph, path with 3 vertices, and I'm going to compute x of g. Well, let's start off real simple. What if we're only going to use the colors 1 and 2? Well, in that case, there's a couple of ways to do it. I could put 1 at the endpoints and 2 in the middle, right? That would give me x1 squared, an x1 from here and an x1 from here, and then also an x2 from the midpoint. But we could do it the other way around, right? We could put the 1 in the center and the 2 at the endpoints. That'll give me an x1, x2 squared. And notice we're already seeing symmetry. If I exchange x1 and x2, this part of the function remains invariant. What happens if I use the colors 1 and 3? Well, it's not much different, right? Either I put the 3 in the center and the 1 at the endpoints, or vice versa. This gives us x1 squared, x3, x1, x3 squared. And I hope it's clear now that if I use any pair of colors, I'm going to get these same 2 terms. So I'm going to get all possible terms of the form xi squared xj. Okay, so far so good. But of course, that's not the only way to color this. I could use 3 different colors. What happens if I use 3 different colors? Well, if I say the colors 1, 2, and 3. Well, since I have 3 different colors and 3 vertices, I can slap them on the vertices any way I like, and I'll have a proper coloring, right? Because I'm using each color exactly once. There's 3 factorial ways to put those 3 colors on the 3 vertices. And if I use the colors x1, 2, and 3, they're all going to give us the monomial x1, x2, x3. And then by exactly the same argument, if I use the colors 1, 2, 4, or 5, 700, and 2000, it doesn't matter. You're still going to get all things of the form 6 times xi, xj, xk, where ijk are different. Okay. So our series is symmetric if it's invariant in the under permutation of variables, and it should be pretty clear that this is going to be a symmetric function for any graph, because what does permuting the variables mean? Permuting the variables just means permuting the colors. But if I permute the colors in a proper coloring, it stays proper. So that's all we're saying here. So some background on Simex, the set of all symmetric functions in X of bounded degree. As we've seen before, these are indexed by partitions, integer partitions. So a partition of an integer n, you just have a sequence, lambda 1, lambda 2, etc., of positive integers that sum to n. And since we don't care what order the summands come in, we put them in a canonical weakly decreasing order, and we call these summands parts. So for example, one partition of 10 would be 4, 3, 3, right? 4 plus 3 plus 3 is 10, and they're weakly decreasing. We're also going to need the Young diagram. So in the Young diagram, and this is with apologies to Francois and the other francophones in the audience, I'm going to use English notation here. So starting from that, thank you, Percy, yes, our battle. Okay, so starting from the top and working down, the ith row is going to have lambda I boxes. So as in here. And the reason we need the Young diagram in this particular context is we're also going to need the transpose. So lambda transpose, lambda super t, with parts lambda t1, lambda t2, etc. You just take that geometric Young diagram and transpose it around the main diagonal like you would a matrix. So the rows become columns and vice versa. So there's the transpose. So right, these first three boxes become the first row and etc., giving you 3, 3, 3, 1. Okay, so hopefully this is all nice review. So what we're going to do is we're going to relate this chromatic symmetric function to two very classical graph theory invariants. So let me introduce those now. So suppose I've got a graph and I've got a subset of the vertices. That subset is called independent if there is no edge between any pair of vertices in the subset. Okay, so if this is my example graph, then for example, UW is an independent set because there's no edge there. And if I had more vertices in the graph, I might be able to add more, again, without ever getting an edge. Why should independent sets have anything to do with this subject? Well, if you think about it, if I've got a proper coloring and I look at all the things that have a given color, I, so C inverse of I, if you want to be formal about it, that's got to form an independent set, right? Because if I've got all the things colored I, you can't have an edge between them because it's proper. Okay, so what we're going to care about is what's called the independence number of G, which is traditionally denoted by alpha of G, and it's going to be the maximum number of elements in an independent set. Okay, so for example, alpha of this graph is 2. I've already shown you an independent set with 2 elements. And why can't you do any better? Well, you've got this triangle here, UVX, right? All of these are adjacent to each other. So if I have an independent set, I can take at most one vertex from the triangle and then perhaps W. Now we're going to go to the other extreme. A subset of the vertices is a clique if whenever you pick 2 vertices from that subset, you always have an edge between them. Okay. So for example, as we just pointed out, UVX here is a clique. It's a triangle. They're all adjacent. And then we have omega of G, the clique number, which is the maximum number of elements in a clique of G. And I claim omega in this graph is 3. Well, again, here's a clique with 3 vertices, and clearly I can't throw in this vertex and still have a clique. So just remember, alpha of G, independent sets, no edges, alpha being the first letter of the Greek alphabet, omega of G, last letter of the Greek alphabet, all possible edges between vertices. Okay. So monomial symmetric functions, the easiest possible basis, m sub lambda, you just sum all the monomials that have, if you look at their exponent sequence as a partition, have lambda as that exponent partition. So for example, M21, you just sum all the things of the form xi squared xj, as we saw in x of g for the path. And now, crucial definition for us, suppose we have any basis for the symmetric functions, b lambda, and I have a particular symmetric function f of x, then we'll say a particular basis element, b mu, appears in f. If you expand f in that basis, then the muth coefficient is non-zero. Now notice, I'm not saying it's positive, I'm not saying it's negative, I'm not saying it's an integer, I'm not saying anything except that it's not zero, that it exists. So here's a simple observation that we use for our results. So fix a given lambda, and suppose that m lambda appears in your chromatic symmetric function. Which m lambda can actually appear? Well, two conditions. One is that the maximum size of an independent set has got to be at least lambda 1, the length of the first row. And kind of dually, the maximum size of a clique is at most lambda transpose 1, the length of the first column. Now, this is really easy to prove, so let me show you the proof of A, and B is similar. So think about it. If m lambda appears, then in particular, the monomial x1 to the lambda 1, x2 to the lambda 2, etc. appears. But that means we have a coloring where the color 1 is used lambda 1 times, right? And we said that for any color, if it's used that many times, that's an independent set. And alpha is the maximum size of an independent set. So if we have some independent set of size lambda 1, then obviously the maximum is at least that big and maybe larger. End of story. Okay, so hopefully this is really simple. That's one of our points, that going via the monomial basis is going to give us power when we get to the elementary basis. So let's talk about the elementary basis. Elementary symmetric functions are defined in two parts. First, E sub n, for a positive integer n. You just sum all the square-free monomials in x of degree n. And then to get E lambda for a partition, you just take the product of the individual E sub lambda i's as defined in the previous line. So for example, E sub 3, you'd have all things of the form xi, xj, xk, where ij and k are different. And then for E433, we would just multiply E4 times E3 times E3, where E3 is given above and E4 is should be pretty obvious. So here's one of our theorems. We've been using this enough that we've given it a name. We're calling it the alpha omega theorem. Suppose now we fix our view on a given lambda, and we want to know whether E lambda appears with non-zero coefficient in x of g. Then everything kind of gets turned on its head. Omega of g now is bounded above by lambda 1 rather than below by lambda 1 transpose, and vice versa for alpha of g. And again, this is really easy to prove, so let me prove it for you. What does the basis change matrix look like? Well, it's triangular if you use the right orders on the partitions. In particular, m sub mu is just a sum of E lambdas, where lambda is greater than or equal to mu transpose, where this greater than is lexicographic order. If you wish, you can use dominance order, but we won't need that. Lex order is enough for us at this point. Okay. So if E lambda appears in x of g, then so must mu that contributes to that E lambda, right? Because if none of these have E lambda in its expansion, then it's not going to get there. But that means lambda's got to be greater than or equal to mu transpose, and I've just written this in the reverse order of the inequality. But now use the previous result, right? by the previous result, omega of G in the M basis is at most the first part of mu transpose. But for this inequality, lexicographic inequality to be true, clearly their first parts have got to be in the same order, because if the first part of mu transpose is bigger than the one in lambda, they have the opposite lexicographic order. So we're done. Okay. So our basic motivation here is the Stanley-Stambridge conjecture. So let me tell you about that now and show you how you can make some progress on it using these ideas. So usual notation, brackets mn is going to be the integers from m to n, and if m is 1, I abbreviate that to brackets n. Then a natural unit interval graph, and all of my graphs are going to be natural unit integral graphs, so I'll just say interval graph. It's a graph of the following. Its vertices are the numbers 1 through n, and if you take any edge, ij, and I'm always going to write my edges with a smaller vertex first, the whole interval from I to j must form a clique. You must have, if you have an edge from I to j, you have an edge between any two pair of vertices inside that interval. So for example, this is an interval graph, right? Because if I look at the edge 1, 3, then all the edges inside 1, 2, and 2, 3 are there. But this isn't, right? Because I have the edge 1, 4, but that would imply, if it were an interval graph, that I should have 1, 3, and 2, 4, and they're not there. So now we're going to worry not just about appearing, but the sign. So I've got my basis, I've got my symmetric function. We'll say that the symmetric function is B positive if every single B mu that appears, every single one of them does with positive coefficient. And so the Stanley-Stambridge conjecture, which was then refined by Guy Paquet, is that if G is an interval graph and I expand Xg in the E basis, it's E positive. And there's been tons of work on this, both from the combinatorial side and using algebraic geometry and so forth. So let me show you one of the things we can prove. Suppose we've got an interval graph, and suppose lambda 1 is at most 3. So the diagram has at most 3 columns. Then the coefficient of E lambda in X of G is always non-negative. Now, another point I want to make it right now is a lot of the work that's been done on this conjecture has been of the following form. Take some subset of the interval graphs and show that they're E positive, right? So specify more the graph you're looking at, and then show that all of its coefficients are E non-negative. Our method turns that on its head. Rather than looking at a specific type of graph and looking at all of its coefficients, we look at a specific coefficient, right? In this case, the E lambdas where lambda 1 is at most 3, and show that it's got to be non-negative in all the interval graphs. So kind of a dual approach. And this turns out to be really easy because the hard work has been done by somebody else. So, right, from the alpha omega theorem, if E lambda appears, then omega of G is at most 3. Remember, omega is the clique number. That's how saying the max. Yeah, these are very restricted graphs. The biggest your clique can be is a triangle. Or if I want to translate this into interval graph terminology, if I've got an edge between I and J, the difference between I and J, this absolute value is B at most 2. These graphs have already been studied in a paper by my former graduate student, Samantha Dahlberg, and she proved that these interval graphs are always E positive, these types. So essentially what we're saying is either you're in the graphs that Dahlberg has studied where we know they're E positive, or in all the other ones, it's 0. So you don't have to worry about it. That's what's going. Okay, so I think I have enough time to give you some comments and statements about other work, because we're not the first people to use this basis change idea to good effect, but I think it has been overlooked by the majority of people working in this area. So let me just give you some sense of some of the other, I just gave you one result. Let me show you, or at least talk about a few other ones. Changing via the basis M. So we're always headed for the E basis. First of all, we can strengthen the alpha omega theorem using basically what I would call an analog of a Green's invariant. So rather than looking just at the length of the first row or the length of the first column, you look at the lengths of you add the lengths of the first I rows of the first j columns. There's a corresponding theorem there. You can also get results for other shapes. Here's an example. Suppose I have an interval graph and lambda has the following form. It's some partition mu, which is at most a partition of a number at most 10, and then add a tail in the first column, as many boxes of length 1. The coefficient of E lambda xg is always non-negative for these types of partitions. But you could say, wait a minute, there's lots of other bases to go by there. I mean, why pick the M basis? Why not try other bases? And indeed, you can, yes, obvious question. So maybe Percy was going to ask it, I don't know. Anyway, what if you go, say, by the Schur basis, one of my other favorite bases, and you get nice things coming out? So for example, it's well known from the work from Stanley's original paper that if I look at the coefficient of E sub n, so a single part, single row, in X of G for any graph G, does not have to be an interval graph. That's just the number of acyclic orientations of G having a single sync. So obviously this is non-negative, right? It's counting something. So using the Schur basis as intermediary, we can give a new interpretation of this coefficient in the specific case of interval graphs using certain tableaux called p-tableaux that were invented by Vesko-Gasharov to prove the weaker statement that for interval graphs, it's at least S positive in the S basis. So P here is a poset. There are other people that have used this idea going via the S basis. So Sujin Cho and Ha have proved the Shereshian wax Q analog of the interval graph conjecture. So in the Shereshian wax case, there's this new parameter called the ascent number of a graph, and you use Q to the number of ascents. They have been able to prove it for posets P of height at most 2. And then with another co-author, Hong, they were able to prove it for things, the original conjecture, when Q is 1 for height at most 3. And very recently, Wang has used the inverse Koska matrix as the basis change element to make progress in height 3 for arbitrary Q. And I think that's all I have to say. So thanks so much for listening.